Okay, let's dive into a really fascinating evolutionary quest. You see, engineers have spent well over a century trying to mathematically predict exactly when complex machine parts will break. Welcome to this explainer. Today we're going to unpack one of the absolute most critical challenges in solid mechanics and engineering. It is a wild journey that takes us all the way from basic, simple geometry right up to advanced energy envelopes. And honestly, understanding this means understanding exactly how we build our modern world safely.
So, we have to start with a high-stakes dilemma. How on earth do we translate a super simple testing outcome into a cast iron guarantee that a multi-directional real-world part will survive under extreme pressure? Think about it. Every single time you fly in an airplane, drive over a bridge, or operate heavy machinery, your physical safety depends entirely on an engineer's ability to answer this exact question. But as you're about to see, finding a universal rule for failure, it isn't as simple as just testing a piece of metal until it snaps.
Because right off the bat, there's a massive gap. We call it the hypothesis gap. It's the huge difference between an easy one-way pull test in a lab and the complex 3D forces twisting an actual physical component out in the wild. A simple one-dimensional, uniaxial system is totally predictable, right? We just compare the load stress directly to the yield stress. Pretty trivial. But real-world components, like a heavy-duty structural bracket, experience biaxial and triaxial loads. They are being pulled, twisted, and compressed all at once from a dozen different angles. You simply cannot mathematically compare a 1D test directly to a 3D stress state without some kind of unifying theory. To bridge this gap, we absolutely need mathematical boundaries.
But wait, before we can even build our mathematical boundary, we have to recognize that failure diverges completely based on material properties. Think of snapping a really dry piece of chalk versus pulling a piece of sticky taffy apart. Brittle materials, like the chalk, fail through a direct, clean separation. Ductile materials, like the taffy, fail through a slow, gradual process of particle slipping and plastic deformation. So right out of the gate, we cannot treat all materials the same.
And when you look at this at the atomic level, the difference is striking. Brittle fracture happens almost instantaneously. The atomic cubes just separate cleanly with zero plastic deformation. Bam, it's broken. But with ductile failure, the material actually stretches and deforms first. The atoms slip along these 45-degree sliding planes, causing what engineers call necking, which is basically an elongation before a gradual failure. Ultimately, we must classify our material before we can accurately predict how its atomic structure is going to surrender under a heavy load.
All right, phase one. Stress and strain boundaries. Let's look at the historical foundations.
Going way back to the mid-19th century, the first pioneers attempted to draw the very first mathematical safety boundaries. Accredited to British engineer W.J.M. Rankine in 1850, we get the maximum principal stress theory. Now, this oldest theory created a perfect mathematical square boundary. Rankine hypothesized that failure occurs simply when the maximum principal stress reaches the elastic limit that we found in our simple tension test. And hey, if you're designing heavy cast iron machine bases, this brittle fracture boundary is your foundational tool. It works. But as engineers started using more ductile materials like steel, well, they quickly noticed the square was just a bit too simplistic. So Saint-Venant comes along and attempts to improve this by factoring in Poisson's ratio, basically shifting the focus from stress over to maximum principal strain. Adding this ratio totally distorts our perfect square safety zone into a slanted rhombus, which creates cross-axial dependency. It remarkably predicts that if both principal stresses are pulling in tension, the material can safely exceed its standard yield point. No way, right? But it's true. This works great for thick-walled glass or ceramic pressure vessels, but yet again, empirical testing proved it remains super unreliable for ductile metals. The math simply wasn't matching the physical reality of steel.
Moving right along to phase two, shear boundaries. This is where we enter the ductile design paradigm.
Engineers soon had a massive realization. Straight pushing and pulling wasn't the main culprit for ductile metals at all. Actually, shear is what drives ductile failure. Jointly accredited to Coulomb, Tresca, and Guest, this theory radically shifted the perspective. They realized failure under biaxial states happens specifically when maximum shear stress equals the shear stress at yielding. Derived from the really striking geometry of Moore's circle for stresses, this gives us a critical, game-changing prediction. The yield strength in shear is exactly half of the yield strength in tension.
Now, when plotted for biaxial stresses, these equations form this beautifully distinct hexagonal boundary. What's absolutely fascinating here is how the Tresca hexagon fits entirely inside our earlier Rankine square. By sitting well inside those outer limits, it provides a highly conservative safety margin for ductile parts. If you're out there designing steel transmission shafting for heavy machinery, where an unexpected failure carries a catastrophic risk, you want this conservative hexagon. It guarantees a margin of safety you can literally bet your life on.
Next up, Phase 3, Energy Boundaries, the real quest for maximum precision.
As engineering rapidly advanced into the 20th century, materials got a lot lighter and tolerances got way tighter. We fundamentally had to shift our metric from directional forces pushing and pulling to stored scalar energy. Hay proposed that inelastic action begins only when the total energy absorbed equals the energy absorbed at the elastic limit. This introduced a really cool tilted ellipse envelope that crosses the axes. This paradigm shift gave engineers a highly accurate, orientation-independent safety region. It proved incredibly useful for complex load analysis in non-ferrous, thick-walled cylinders.
But the real mathematical breakthrough, the absolute genius moment in failure mechanics, came sequentially from Huber, von Mies, and Henke. They realized that total strain energy was actually an incomplete metric. Why? Because pure hydrostatic pressure changes the volume of a material, sure, but it doesn't cause it to yield. Imagine you're squeezing a solid block of metal equally from all sides deep down at the bottom of the ocean. It shrinks a bit, but it doesn't break. So they mathematically separated the total energy into two discrete physical components. Total stress equals the stress due to distortion plus the stress due to a change in volume. Materials yield because they are twisted out of shape by distortion, not just because they're uniformly compressed.
And this amazing realization gives us the von Mises ellipse. It forms a perfect mathematical boundary that tightly and beautifully encloses the more conservative Tresca hexagon. Honestly, it is the undisputed gold standard for precision engineering today. Because it perfectly predicts ductile failure, it eliminates all the overly conservative fat of the hexagon. That is exactly why this precise ellipse is the go-to mathematical boundary for designing lightweight aerospace aluminum components. When your factor of safety is held to exceptionally close limits, so a literal rocket can fly safely into space, you rely on von Mises.
And finally, the ultimate boundary, where context is literally everything. When we layer the entire history of our quest onto a single graph, it reveals exactly how these boundaries interact dynamically. We've got the brittle Rankine square on the outside, which is ideal for cast iron. Nestled securely inside is the conservative Tresca hexagon, the absolute safe bet for heavy steel machinery. And hugging the edges of that hexagon, perfectly cutting away the unnecessary margins, is the precise von Mises ellipse for aerospace aluminum. The final takeaway here is incredibly clear. Master the boundary, and you master the design. No single theory magically governs all materials. True precision engineering requires you to meticulously match the mathematical hypothesis to the physical reality you hold in your hands. So, knowing that our safety boundaries have evolved over centuries, from a basic square in the 1850s to an inscribed hexagon to a perfectly calculated distortion ellipse that literally puts humanity in the stars, it definitely leaves us wondering. As we engineer entirely new metamaterials, things like carbon nanotubes and insanely complex composites, what new geometric perfection might the future of material science reveal next? We have conquered the square, the hexagon, and the ellipse, but the quest for the next perfect boundary? Well, that is far from over. Thanks so much for joining me on this explainer, and remember to keep questioning the boundaries around you.